Good afternoon. I'd like to start out by thanking all of the speakers today. They were fantastic. I learned a lot. I've been in technology my whole life, and I'm very impressed with the forethought as well as the outlook in the current products that people are bringing to market or attempting to bring to market, the projects that are going on, as well as the theoretical discussions as an industry as to where we're going and where we're looking. Just a note to the hotel staff, the Angry Birds in the first elevator is not working, and would someone solve Angry Birds in the second elevator, because I'm just tired of missing it. I'm on the 6th floor. If I was on the 10th floor, I'd get it. I'm probably the luckiest guy in the room, and gal in the room. 2 years ago, a gentleman at the end of the hall called me when I was standing in a field in Italy and said, "I've got that money you want. What do you want to go buy?" And as a disruptive technologist who's been around since the late 70s, spending my whole life telling people, yeah, it really does do that, I was given a golden opportunity. And from that field, I said, let's go buy MTiX. And today we're going to tell you why that was so good. And by the end of the day, you will realize I'm the luckiest guy in the world. We now have a company that controls an amazing technology, one which will change a lot of industries, including the textile industry. And we're going to talk about that today. Who here has been in a textile mill? We're all from the textile industry, but who's been in a mill? Okay, about 50% of the room. So you've all seen washers the size of this room, or stenters the size of this room. Those of you who haven't, get to your nearest textile mill. It's hard to be in an industry without understanding what really goes on. Innovation has to happen at the core sometimes, because putting innovation just on top is incremental steps. It's not quantum leaps. And so if you don't know what happens at a mill, and you haven't seen the amount of water that goes in, and you haven't seen the amount of people that touch the fabric, if you've never been to a shoe factory to see how your shoes are made, it is just absolutely amazing. You'll never get dressed the same way again. Someone ties these shoes before they go out the door, polishes them, hand fixes the glue on there. It's amazing as what goes into textiles. MTiX is a material science company focused on sustainable substrate synthesis. And that is a key word, synthesis. Changing the basic core and nature of the fabric. Jar's going to talk about that. What does that mean to the world? Well, to talk about that really quick, I want to step back 100 years. Who in here remembers the first TV they saw? Okay. The younger people don't. It's ubiquitous. Someone talked about ubiquitous technology today. For younger people, they grow up with screens all around them. Laptop, phone, TV, your refrigerator has a screen in it. But for some of us, the first screen we ever saw, your parents brought in, or my parents brought into the house, and it was black and white. And they turned it on, and you saw an amazing thing, a live picture. Now, snow, yes. How many of those who saw an original TV or one of the first ones were black and white? And how many of us put our face up against that glass to see what was behind there? And what was that thing? What was that thing that was making a picture? It was pretty big at the time. We call it a pixel now, but it was a black and white dot. Right? And so I'm going to talk for a few minutes about the power of that dot and how it changed the world. And it's interesting, we're rethinking materials today, and what's the logo? The dot. Think back 100 years. There were some scientists, most of us don't know their names. They were pointing a gun, an electron gun, at a screen, phosphorus screen, trying to make one thing happen. This beam of energy turn into a dot. And once they got the dot there, they went out and had a beer or drink, Now they had to do something even more important. They had to move it. They had to put it anywhere on that screen. They had to control the dot. Now, once they could control the dot, what happened? Race forward 100 years. CRTs came out, oscilloscopes came out. We had displays. That dot became text. That dot became pictures. That dot became colored. Now, it really wasn't all the colors in the world. It started as 3 colors, red, green, blue, RGB. So the dot had one parameter to begin with, on and off. Then it had a color parameter, and we could trick our brains into thinking it was really color. But that dot changed the world. It changed the way we communicated. It changed information. But it didn't really do anything. It never changed the surface of the screen unless you left that Pong on forever, and then you got lines across the screen. What did it really do? What did it really change? But it changed everything. It allowed and enabled everything we've seen to move forward. Okay? So Jar is going to come up here and talk about a different dot. He's going to talk about the MLSE dot and what it means to textiles and how it has more parameters than just on or off. Or what color is it? And how it changes the textile, not just presents information. Okay, Jar?
Thanks, Phil. I'm going to skip around a little bit. The content might seem a little disorganized, but it's really just to be able to set the right understanding so that you can accept and digest the information I'm going to try to give you today. So I'm going to start by looking at one of our current platforms in its final testing so you can see the platform that we're talking about. Oh, I thought there was sound, but it's just our current platform as it exists today, and that system is currently in final testing and waiting for its customer to finish their site preparation so we can go and install it. Now stepping back to our initial iteration of the technology, you can tell it's quite different, very modular, so we could move things around and figure out how everything was going to work together. Almost 8-9 years ago now, and it was really a labor of love. We spent a lot of time working the technology out on this system here. We worked with the Textile Center of Excellence to put it all together. They gave us a place to assemble the equipment, gave us some personnel to help us get through and do testings and everything. They also helped us by organizing some third-party people to come in and validate what we were doing. And they took some of our fire retardancy materials that we had processed, and they compared them against industry standard fire retardancy materials. And here's what they found in the process, that our process used more than 99% less energy, that our water consumption was 75% less, that our the resources, the chemistry that went into it, 94% less. Really, really staggering. I mean, we knew we were onto something, but I don't know that we hadn't had the ability to quantify it. And when we got this report, it was just it was really exciting. So jumping back now to a few iterations later, our current platform, we've made a lot of changes. We've been able to speed up the machine to keep up with certain finishing processes. The machine can process fabric at up to 70 meters a minute. Our platform is finish agnostic. We can produce virtually any finish that's necessary, and I'll get into what some of those finishes are in a little bit. We can handle any kind of material, stretch materials, wovens, non-wovens, man-made, natural fibers, whatever. We've got a new delivery system of our reactant chemistries that go in there. That's very controllable. We can do atomic layer deposition. Does anybody in this room, is there familiar with, we got 1, 2, all right, about 4. Atomic layer deposition, for laymen, is the very precise control of the amount of particulates that we want to put down. We can control it to the atomic level. Oh, I'm sorry, I'm hitting the wrong button. So some of our processing results to date. Some of these aren't very special, but that's okay. Our system does everything. I think some of the notable things are on here that are texture and feel. We control that. We can make certain fabrics feel different. We can take, call it cheap wool, and make it feel like cashmere. We can make things stiffer or softer, whatever's required by our customers. We can also, a lot of that's through managing the surface topography. Enhanced adhesion for applications such as automotive seats. Anti-pilling so that your cashmere stays looking nicer longer. Antimicrobial without silver particulates. Dye efficiencies. That's pretty easy. Fire retardancy. The important thing about our fire retardancy is that we don't use bromines or bromates. We don't use any noxious or harmful chemicals. And we achieve some pretty remarkable results. This is an example of one of our licensees doing a test. This test, the flame stays on for 15 seconds and then retracts, and the test is complete when either the material burns up or self-extinguishes. And you can see as soon as the flame is removed from our material, treated on the left, the test is over. The untreated is on the right. Not a good day. Hopefully that's not your couch. Similar results across a spectrum of materials. Wool, nylon, cotton blends, Nomex, silk. Hydrophobicity, water resistance. It's kind of hard to see with the contrast, but excellent results. Notable thing here, no fluorinated polymers, no long carbon chains. Nothing harmful, nothing noxious, nothing that you don't want on your skin. We don't need to watch the whole thing. It stays dry. Wool scouring. These are some of the original images from some of the original work we did on textiles. On the left, you can see raw wool covered in lanolin, fatty acids, and with some very basic parameters early on, we were able to find out that we could almost perfectly clean wool in a dry scouring method. Here's some other SEM micrographs of the clean wool afterwards. And this is some carbon treatment on the merino wool to further smooth out, remove the cuticles, so that you have a smoother wool that doesn't bunch up on itself as much. Increased strength on polymers. So let's rewind the clock and let's talk about what MLSE is at its core. In order to do that, we need to talk about how MLSE, the ingredients, the constituents that led up to MLSE, which is innovation and invention. The team of MTiX has been working together and has a history dating back 85 years. And that history goes all the, sorry, I've got some notes actually. And if anybody's interested, you can turn to page 10 in the pamphlet that's on your table. It's the last page. But in 1933, we patented the analog forerunner to CNC, computer numerical control. In the 1940s, that device was called the tracer, and it was used for controlling automotive and aerospace machines. In the 1950s, we used computer numerical control for aerospace components. In the 60s, it was the first numerically controlled machine tool in the automotive industry. Ultra-high-speed machines in the 1970s, pioneering the ultra-high-speed machine technology, enabled things like the Tomahawk cruise missile and space shuttle tiles. In the 1980s, we eliminated carcinogenic coolants that were used for metal cutting, so that not only were you not exposing yourself or your employees to harmful carcinogenic coolants, but now you could take those aluminum chips and recycle them for ingot value. And our manufacturing systems would pay for themselves within 18 months. In the 1990s, we invented MLSE. And I'll get into more what that is, but it was really all those things prior to that that led us into MLSE. MLSE became a way to enable further technology. And then in the 2000s, we applied MLSE to textiles. So here's a diagram showing, it's this very simple diagram of MLSE and its origin using multiple wavelengths of lasers in a rarefied atmosphere to change the blue steel into black diamond, an industrial diamond. And essentially that's what we did. We had hundreds of patents on using these multiple energy sources in a rarefied atmosphere to synthesize thin film diamond on the surface of metals, polymers, ceramics. And it wasn't a thin coating. It wasn't like the industry standard of the day, which was CVD or PVD, which was just a thin coating on the top that could spall off, crack, get scratched off. But it was a transformation of the material. We were stealing carbon out of the steel or plastic and embedding it back in as a changed material. Some of the key early applications were, I already mentioned the high volume, the high speed aluminum machining. One of the enablers was being able to, was diamond because of the thermal transfer properties. Inkjet pens for printers and ophthalmological surgical knives that a treated steel knife could now outperform an actual 100% diamond knife. And we had these manufacturing cells that we make and for treating those types of steel or polymers or ceramics where your MLSE is happening at a point. The diamond that's synthesized, we could do various structures and shapes and control it. We could planarize it. We can do it on Cermet materials. Here's a close-up of the diamond as it transitions into the tungsten carbide. More diamond examples. We could do a lot more than diamond, but it was always the thing everybody wanted to talk about because making diamond out of thin air is just really cool. So what is really going on here? What is this magic ray gun, as a lot of people used to call it before they could really understand it, before we could explain it? So, and I've got some notes here because it does get a little complicated. The process of MLSE is controlled by a process algorithm, and I like to define it as a measure of the constituent inputs for a reaction chamber where the energy parameters required to disrupt that incoming textile from its natural state and subsequently rebuild it into a new desired state. Now, the process itself, in our MLSE platform, we start by getting that chamber warmed up to the proper thermal equilibrium. The atmosphere in the reaction chamber is then rarefied so that only the desired elements are present. And then that rarefied atmosphere is ignited with high voltage energy, and it's coupled with a severe photonic radiation. The resulting amplified photonic energy arising from electrons changing orbits creates virtual particles. Does anybody know what virtual particles are? This guy, he's got all the answers. So, for those that don't, the simplest way I can think to describe it is an electromagnetic force, the feeling you get when you're trying to push two magnets together that don't want to go together, can be described as an exchange of those virtual particles or virtual photons. And that might not be the best description, but that's the best layman description I can come up with. So our unique optical configuration allows for a regenerative amplification of the energy and the increasing efficiency that further accelerates that virtual particle interaction. Now the textile is delivered into the chamber, which is another part of the ingredients. It's another constituent that goes in. Solids, liquids, gases, ionized energy, the laser, they're all parts of the process algorithm. The process chemistry is controllably entered into the reaction milieu and is drawn in and combined into a highly energized soup, if you will. And that is expanded and compressed and coupled with the now activated substrate. The excited electrons are brought to their quantum limit, and electrons are ripped from the atoms as we empower structural alteration of matter and enable novel material synthesis. The pulsed UV laser accelerates compression of the the pulsed UV laser accelerates compression of the programmed highly ionized and reactive stoichiometry into the structure of the fabric's finish. Now, there are 4 distinct reaction zones or reaction chambers in our MLSE platform. They can all work in concert with each other, doing the same job to either intensify an effect, or we can control them separately with different process algorithms and in effect have each one doing something different. We can also affect both sides of the fabric in a single pass, resulting in a multi-treatment, double-sided in a single pass, and in some cases it speeds up to 70 meters a minute. So I've used the word platform a few times, and Mark used the word platform, and Anna was using the word platform, and I'm so glad they did. They kind of broke the ice for me on that. What we have here is really a platform because we can accept virtually any input, we can affect virtually any output, because it's a platform. And we use some of these applications, if you will, that we've shown you with hydrophobicity, fire retardancy, stain resistance. We're showing you those applications as an example of some of the capabilities of the system. But if I can liken it to Apple's iOS platform and one of their original marketing ploys where, somebody's like, oh, check my heartbeat on my phone. Yeah, there's an app for that. Fire retardancy on silk, there's an app for that. It's pretty great. Sorry. Now, if I could ask Phil to come back up.
I hope you save that piece of paper and memorize your description. I don't know that I will ever. But if you heard a TV described 100 years ago, or even 50 years ago, and asked what's going on in the chamber at the time was a vacuum tube, a CRT, with an electron gun in it. but they'd captured the dot. They could create a picture on a screen. Early in the 1990s, the team at MTiX and the scientists captured a dot. They could apply it to steel. You saw the robots in these pictures which wrapped that dot physically around the steel, changing that steel, transforming that steel into a diamond-coated surface or the surface. And that was used and is used in microphones, in automobiles. For the space shuttle, tiles of science was used. It was used for knee joints, scalpels. It's amazing how that dot just changed the metal world. Previn Mistry, the man who invented the dot, who's an incredible, brilliant guy, figured out a way to extend the dot. And the team worked to make that dot go 3 meters wide, or 2 meters wide, working on 3.2. And allow software to change that dot as the fabric moves through the system. On both sides of the fabric, 4 chambers, 4 dots. What does that mean? I mean, it's great to hear all those atomic elements moving around and all that science. But what it means fabric like this. That's water resistant with no fluorocarbons. It's been synthesized. Feels like the fabric of this shirt. That's without MLSE. The difference is there are no toxic chemicals in this. The water consumption used to finish this fabric was substantially less. The energy was 90% plus less. That's huge if you've been to a textile facility and seen a washer the size of this room. These shoes were made by our research partner, Inoscope, out of Alicante, Spain. They spend their lives, 100 scientists or so, researching shoes. You never could imagine what goes into a shoe. I mean, it's absolutely mind-blowing. They're fire-resistant shoes, protective wear, with no bromines or bromates in it. Jar talked about the feel of the fabric. We had one of our licensees say, you know, that's great that you have no toxic chemicals in it, but our fabric used to be a little stiffer because of the toxic chemicals. Could you not use toxic chemicals and could you make it come out stiffer? Because our cutting machines and our sewing machines all are set to the stiffness that it used to be. Answer, yes. So MLSE, when you think of what happens at the dot, a change to the surface, making that surface something it wasn't, and keeping the properties of that surface what you want. All of a sudden, you connect that to the dot on the TV screen and how it changed the world, and all of the implications it made. So we're an enabling technology. We're a tool, as Jar said. We're a tool for the textile industry. We aren't textile people. The artisanship that goes into making a textile isn't lost. Right now, the artisanship is someone coming to a textile manufacturer saying, hey, I'm making a shirt. I want it brown, I want it to feel this way, I want it to be almost see-through, I want it to be this. And some expert within the textile facility says, you know what? The process to make that fabric the way you want it, that machine, those chemicals, this amount of water, that dryer, at this temperature, is it what you want? It's an art. It's an art to making a textile. If you don't understand that, get to a textile mill and watch the people work. They're artists, okay? That artisanship's not going away. No more than when technology replaced people who used to do layout for magazines. When we used to do magazines, raise your hand if you know how a magazine used to be made. Taking a picture, putting it on, cutting it, and pasting it to a form, and then taking a photo for the magazine. That's where cut and paste comes from. in a computer. Most young people don't know that. You used to actually physically cut and paste and glue. When desktop publishing software first came out, all of the desktop publishers thought, or all of the publishers thought, oh, we're going to lose our jobs. And what they found was when pixels were this big, Phil Mansour could print a card. Phil Mansour could print a catalog because they were black and white and they were about this big. When they got small after a few years, and there were 16 million colors, guess who needed the new tool? All those artists who used to do it, used to be able to say, hey, that's in the wrong space. They were just doing it on a new tool. We have a new tool. What that tool can do, the textile industry will tell us over time. We can do a few things with it now. We're rethinking the way business models work. But the real magic of that tool is yet to be seen. So let's go to the next slide. And I'll finish up so that we can answer questions and you can get on with your day and the award ceremony. Rethinking manufacturing. Waterless finishing. Non-toxic. Zero discharge of toxic chemicals. If you're curious about the current state of MLSE and its current package and how it works, that machine you saw that's in the video, get with one of our people. The engineer behind it, Graham, is here. He can answer all your questions about thickness, about fabric, about stretchiness, about all the different things associated with running and how easy the machine is to operate, iconically based, etc. It's fast. It's faster than most processes. If you've ever seen fire retardancy applied slowly, goopily to fabric as it goes through and then goes through a 110-foot dryer, this is pretty fast, up to 70 meters a minute. It's efficient and it's flexible. It's a push of a button. We're digitizing this process. You can go water resistance to fire retardancy with the push of a button. You don't even have to change the system. You don't have to clean anything out. There's no what do you call them? Bins to wash out and waters and chemicals to remove. The chemicals and the science all happens at an atomic level. And now we have constantly changing regulations. Governments who are saying, hey, this chemical's outlawed, this process is outlawed, this item is outlawed. We have a platform now that changes from a software perspective, a process algorithm perspective. So if a standard changes, we can change with the standard without changing hardwares or chemical companies or worrying about it. It allows the textile industry to move forward in a different way. Oh, this is down here in front of me. I can look at you all. So materials and uses. Design is going to change. Someone was talking about that earlier today. Brilliant presentation. What does the change in textiles or enabling technology do to how we think about things? I'll give you one example. It wasn't in this video, but we have some videos of fire retardant silk. Now silk, traditionally, if you try to make it fire retardant, it doesn't feel like silk. You wouldn't want a bed sheet made out of it, right? Everything in this place has to be fire retardant by the local codes. Codes are different everywhere. Silk is never used as a barrier in this room, so sound could pass through, but you could feel like you're in a different space. Why? It's not fire retardant. It goes up really fast, very fast. Fire retardant silk allows designers now to use silk in different ways, okay? Using water-resistant materials in different ways. Making leather fire retardant allows it to be used in different ways with no bromines, no bromates, no chemicals. This is huge. The auto industry in the United States alone has 420 million meters a year in interior fabric, all covered with toxic chemicals. And that's only 18% of the worldwide textile marketplace for interior in cars. So call it a couple billion meters a year covered in bromines and bromates, which touching up against your skin and in fires, etc., is extremely toxic. So the need for this is absolutely incredible. But what you can do as a designer now all of a sudden changes. Because if you feel our fire retardancy fabric, and if you want to, I have a bunch here you can feel. You'll feel that the handle hasn't changed. And it sure does not feel like fire retardancy fabric with the back coating on it. Cost-effective digital print on wool or polyester or cotton. So one of the challenges with printing digitally is you've got to get that dot, an ink dot, to stand up on end and fix it in place. And if you do that on cotton, it absorbs. It's hard to print a picture on cotton that's not hydrophobic. So inline systems for digital print and digital print prep of different materials. And new uses for apparel and footwear and protective clothing. And the base substrate that you all, or a lot of you, have talked about for wearables. Did you talk about graphene? No. If you're interested in graphene and what we do with graphene, CJAR. The challenge of this world moving forward is how do we produce materials cost effectively, environmentally friendly, and sustainable? And we have a platform that helps. A tool. Go ahead. Next. And then rethinking business models. On-demand finishing. I heard the other day on BBC, someone was reporting on the textile industry, we've moved from 4 seasons a year to some companies having 52 seasons a year. They just come out with a new line of fabric and clothes every week, which is crazy on the sustaining side. And, but we live in a world where we need on-demand products. This allows us to be more on-demand with our finishing. Some of our licensees in the state of California now, for instance, in the United States, you have to provide furniture or items fire retardant and give a non-fire retardant option. Same fabric, same process, on or off. Licensing versus selling. One of the challenges with our tool is it's very expensive right now. We got a very expensive high-power laser on top of a fabric handling unit with an incredibly high power source inside that unit. And so we found the right financial resources to license this technology. So our customers don't pay for the system with a direct cost. We get a per meter charge based upon the treatment. That treatment cost is usually less than the energy costs and the raw material chemical costs that already go into the materials. We want to work with people and partners to be successful. We don't want to sell a machine which requires quantum physics algorithms to be successful and then have a customer come back to us and say, that's great, but we can't run it. Our operator interface is extremely simple. Our scientists work with your textile engineers to create the necessary process algorithms to run that machine all day long. When you get paid by the meter, you want to run it all day long. So we're successful when our customers are successful. We take care of all of the science of keeping that machine. It's a space-age machine. And it looks like there's plenty that they didn't see. There's an amazing utility farm that drops outside the building with air conditioners, etc. And we keep it running. It runs, you run, we're all happy. You don't have to know the science of lasers or plasma or anything that goes on inside that system. Your operator simply loads the fabric in like any other system, pushes the button and selects the batch and moves forward. So completely rethinking the service model. And then how do we get people, how do we get usage of our technology? Who in here is an MLSE expert? There should be 2 hands going up. Todd, you're not an MLSE expert. Okay? Our challenge is we can't go to Stanford or MIT or anywhere to get these people. You need to know quantum physics. You need to know chemistry. You need to know textile engineering. You're taking an input substrate. You're combining it with inert gases. You're combining it with chemistries and solids, vapor layer deposition, all that stuff. We have to train people on the new science. What good is a computer in 1979 when I said to people, oh, this is a computer, it's going to be on everybody's desk. If we put it on everybody's desk in 1979, it wouldn't run. Someone would say, Phil, you said this was going to do a spreadsheet. Well, spreadsheets hadn't been invented. Someone hadn't taken that dot and said, oh, I can do an accounting on that. But that computer could do it. No one had done it. So we have MLSE Academy that's been created for finishing technology propagation. We're working with academia. We're working with corporate and business partners like Inoscope to provide, and independent developers, to provide a development unit where they can work on their own process algorithms for their own technology, which runs on our machine. We're working with industry to develop the skills to use the tool so they can bring the artisanship and the scientific knowledge to tell us, oh, you know what you can do with that beam? You can make a color TV with that beam. Oh, you know what you can do with that beam? You can do the following things. I'm very excited to see where we go with the dot we've purchased. We work with MTiX International, I'm CEO of, is the holding company out of the United States. We're a publicly traded company. We're planning on uplisting to the NASDAQ or NYSE American in the first half of next year. MTiX Limited is the British company we purchased. It was the science and the patents. We have patents all over the world. And we have the financial resources to move this company forward and propagate this technology step by step by step through the industry with the partners who wish to play with us. Any other questions? Oh, you're the question guy. Thank you.